Hello everyone. So today we're going to be talking about disproof. So up till now in the course, we've been presented with some theorem, some proposition, some true statement P, and we've been trying to find a proof of that theorem P. But now what we're going to be doing is walking back a step, because before any given statement P is a theorem, right? To call it a theorem, you have to know that it's a true statement. But presumably there was some time at which people didn't know that was a true statement. They had to decide whether that statement was a true statement or a false statement, and then upon that decision provide the proof that made it a theorem in the first place. So we're walking back one step to that phase of discovery, trying to decide between P and not P, right? To P or not to P. Because that's just the nature of mathematics. I mean, if you ever do math research, or as you progress in your mathematical education, you're going to meet more subjects, and you're going to start thinking about things for yourself, and sort of exploring and trying to discover new math on your own, and you're going to have various hunches and intuitions and feelings about what possibly is true, and you could call those statements, whatever you think is true, that statement P, and we would call this statement a conjecture. So this would be some statement we would like to prove that we have some intuition or feeling is probably true, but we're not entirely certain. So it may be the case that P is true, but there's some chance that not P is also true. And maybe that's the thing that we end up proving. But and so if we were to provide a proof of not P would be called a disproof of our conjectural statement P. Okay, so so our mental model for what we're talking about here is we have some statement that we sort of think might be true, P, but ultimately maybe we'll end up proving P or not P. Okay, so proving P, that would be a proof of our conjecture. Proving not P would be a disproof of our conjecture. And, in real life, ultimately we just kind of have to feel our way through the situation, have to weigh the evidence, and try to decide based on some sort of hard to quantify factors, which of P or not P is more likely to be true, and then make a stab at proving one or the other. Maybe we try to prove P, don't get anywhere, then you try to prove not P, maybe you don't really get anywhere with that either, and then you sort of bounce back and forth and sort of try to learn more and more about the situation until you find a proof of one or the other. And in general, there's kind of no fixed rules for how to do that, which is just sort of the way things go. And that's all in good fun, and that's part of doing math ultimately. Okay, so to put some weight behind that general discussion, we might consider the following situation. This kind of comes a little bit out of thin air, but let's just suppose that we're considering the function f of n. So n here is going to denote an integer, a natural number or integer. Let's just say integer. And it's this quadratic function, n squared minus n plus 11. I don't know why you might be considering this particular function, but maybe it comes up naturally somehow. And if we take a look at the values that f takes at some integers, we can consider the simplest case for the first few integers, let's say 1 through 10, and look at the values of f on these integers. And you see 11, 13, 17, 23, 31, 41, etc. And what you can notice about all of these numbers is that they're prime. You just take a look there for a second and sort of confirm to yourself that all of those numbers are prime. And so in such a situation, right, if you happen to be in this situation, maybe it's not an unreasonable thing to make the conjecture, so this is our statement P, that for every integer n, this f of n, which is n squared minus n plus 11, is a prime number. Okay, so maybe that's true, maybe not. And right, we certainly haven't proved it. We have some evidence that perhaps it's the case. So let's write down not p, since we don't know which one is going to be the case. And so we have a universal statement here, right? For all n in the integers, it is the case that f of n is prime. So the negation of this would be the existential statement that there exists an n in the integers. So there exists some integer such that it's not the case that this latter statement here. So such that f of n is not prime. Okay, so that'd be our not p. Okay, so just something to sort of notice here is that the proof of not p, at least in theory, seems like it would be easier to prove than p. So maybe note that it's potentially let me say, for emphasis, potentially much easier to prove not p. And that's just because we just need to find a single integer for which f of n is not prime, and then we would be done with the proof of not p, right? So potentially much easier to prove not p, just have to find one number with a particular property. So on the other hand, to prove p, we have to make some general argument that applies to every integer, implying that f of n is prime. So that seems like, potentially a much more difficult task. But bouncing back, on the other hand, to this not p statement, well, there's infinitely many integers, right? So there's a lot of things to pick from. So I don't know, maybe this integer that we're looking for would happen to be really, really stupendously large, though that turns out to not be the case in this instance. So before we go to try to, so putting yourself in the hypothetical, before you would go and try to prove p, maybe you would just want to check a few more integers n. Like maybe you would want to go out to 20, 30, or even 100 or something. Well, maybe that's too big, but at least expend a little bit more effort looking for this particular n that might not make f of n prime. So, and it turns out, in fact, that if we look at the very next integer, 11 here, 11 squared is 121, and then minus 11 plus 11, well, that just gets back to 121. And of course, 121 is 11 times 11. And so that's not prime. So in fact, the conjecture is false. So I guess we can make our proposition. The conjecture is false. And the proof is just that consider n equals 11, then f of n, that's f of 11, that's 11 squared minus 11 plus 11, right? Yeah, okay, you can see the function here. And that's 11 squared, right, which is 11 times 11, is clearly not prime. Okay, and then I guess just to yeah, so this proves the negation of the statement. Okay, so our conjecture in that case happened to be false, and we could figure that out relatively easily by just looking at a sufficient amount of evidence. So we had some evidence that suggested maybe it was true, but then we look at more evidence and we find out that it's false. And so some terminology. N equals 11 here is called a counterexample. Okay, so it's a particular, okay, so it's a counterexample, you know, it's a particular instance of a thing. So in this case, we're just talking about numbers, so our thing is just numbers. In a different situation, it might be different. It might be a set or a matrix or whatever the thing you're looking at. But in this case, it's just this number, n equals 11, and it's an object that makes your statement, that shows that your statement is false. Okay, so it's an example that is counter to the statement that your proposition is making, that your conjecture is making. Okay, so the general situation here for counterexamples. So the general situation would be if you when your P is of the following form. So your P says that for all X in some set, let me see. Yeah, so for all, I guess I need a different letter than P. I was going to say P of X. Whoops. So let me just say Q of X. Okay, so that's your statement. So your statement P claims that for all X and S, some property Q of X holds. All right, so looking at the negation of that statement, that says the negation of the universal is the existential, but there exists some X and S such that not Q of X. Okay. So this X here, this will be your, so if P was false, you would prove that P is false by proving not P. In other words, by exhibiting an X in S such that not Q of X holds. And this X here that you exhibit, okay, so this which needs to be exhibited to prove not P is what we generally call a counterexample. Okay, so as I sort of illustrated the concept of counterexample up here, but this is the more precise general situation that counterexamples come up in. So so it's when you have a universally quantified statement, and then the counterexample is the thing that satisfies the existence statement that constitutes the negation of the statement that you're looking at. Okay, so here's another. So let's look at another little conjecture here. so this time in the realm of sets. So we can look at the following conjecture. If A, B, and C are sets, and so another way to say this is for all sets A, B, and C, then A minus B intersects C is equal to, so it might be, you might just think sort of based on the symbols here that it wouldn't be unreasonable to think that this might be the case. Right, that maybe there's the sort of distributive law for that minus sign over the set intersection. Okay, so again, this is a universal statement. So this, let me see here. So I can kind of rewrite this as for all A, B, and C, which are sets, it is the case that this equation holds. Okay, so you see that's a universal statement. So the negation of it would be an existential statement that there exists sets A, B, and C, such that this equation does not hold. Okay, and so let's just take a look at what we think about the potential truth or falsity of this statement. So what you can do is draw a Venn diagram. Okay, so you got A, B, and C. Okay, and let's see, A minus B intersects C. Oh, that is, so A minus B intersects C, that's here. Let me see. So B intersects C is, yeah, okay. So here's A minus B intersects C. Whoops, what am I doing? There we go. So it's everything except this. Oh, I think I can do some kind of shading. Yeah. Okay. Right. So it's everything in A that's not in there, right? That's not in B and C. Okay. And what about the other set? So you got A minus B. So that's, so A minus B. Oof. Yeah, let me maybe draw another Venn diagram. So there's too much going on in that picture there. So you got A, you got B, and you got C. Okay, and A minus B, so A minus B is, it's everything in A that's not in B, so that's there. And then A minus C, that's everything in A that's not in C, so that's, whoops, I want a different color. Everything in A that's not in C. Okay, and then the intersection is everything that got colored twice. So that would be, right, so that would be sort of this region in red here. Okay, and so you can see that in general, so these two regions look different on the Venn diagram. The red on the right and what's in black stripes on the left looks different. So we should be able to come up with sets A, B, and C that where these these are different. So let's see. So last time I draw the Venn diagram, so we got A, B, and C. And then we should just be able to fill in some elements here. So let's see if we put 1 here and 2 here and 3 here. I think that should do it. So that means that our A, if we take A to be the set 1, 2, 3, our set B, that's everything inside the green circle, that's just the set containing 2, and C, that's just the set containing 3. And then if we just compute all these little pieces here, so B intersect C, that's the empty set, right? So that immediately implies that A minus B intersect C is just A. And then looking at A minus B, that's just the set 1, 3, and A minus C, that's just the set 1, 2, and then the intersection of those two things, A minus B intersect A minus C, that's just the set containing 1, and that is not equal to A. Okay, so we see that these sets A, B, and C are going to constitute a counterexample to the conjecture. So here's a counterexample to the conjecture. Okay, so I probably should have written this nicely in proof form. Right, so let's say, so we could probably just sort of make this into a proof. So we would say, so we add proof in here, we can say consider A, B, and C, defined as these guys right here. Then we compute, so then compute and we just have the computations that we did here. So, and I guess I can just erase, let me just erase that there. So we have those computations. We see clearly that that A minus B intersects C does not equal A minus B intersect A minus C. And so this proves the, whoops, can't spell, proves the negation of the statement of the conjecture. Okay, so not the nicest looking proof I've ever written, at least as far as the organization goes, but the idea is there. So once you find your counterexample, you just have to show why that counterexample works to prove the negation of the statement that you're considering. Okay, so it's not always going to be the case that your conjectures are false. So let's take a look at this conjecture, and I again, don't really know of a good scenario in which this might come up naturally, but it's the kind of thing you might idly amuse yourself with, to try to see whether there are three distinct integers greater than 1 such that x to the y equals y to the z. Of course, this x to the y equals y to the z, we can definitely find solutions if we let x, y, and z potentially not be distinct. Right? You can take all of them to be equal, and then this is a true statement. It's also easy to make this equation true if you allow 0 and 1 to be involved. So for example, you can do 1 to the 2 equals 2 to the 0. So that would be too easy. So we'll make it more interesting for ourselves and restrict our integers to be greater than 1. And then we have to, in order to prove this, it's an existential statement, so we just have to exhibit these integers x, y, and z. And so we have to figure out how to find them, and it might not be clear how you can do that, but you can try something like the following. So you can, so let's say, let's just for simplicity, let's say x is equal to 2. Just try out, fixing one of them. So you just have to find the other ones. And maybe this works, maybe it doesn't. We'll see that this happens to work in this case. We're just going to try something to get a feeling for what's going on here. So we have 2 to the y equals y to the z. So this left-hand side is all just a big product of 2's, right? And so on the right-hand side, this indicates that this y is also going to have to be a product of 2's as well, right? So this here is just a big product of 2's. Right? And so our y is some integer, and if you think about the prime factorization of that, if that involves anything other than 2, then you're going to have a product of 2's equaling something which has other prime factors, and that just wouldn't work. So this indicates that we should guess. So we should guess that y is equal to some power of 2 as well. So so 2 to the I don't know, let's say to the t. Okay, so we should just try. So now we fixed x, and we have some better idea of what y should be if this is going to have any chance of working out. And then we can kind of work through these powers of 2 and see if we can make this work. So we might try. So the first power of 2, t equals 1. Well, that would give y equals 2, but x is 2. So that's not going to work because we need them to be distinct. So we would move to y is 2 squared. So we would have 2 to the 4, and that equals 4 to the z. But 2 to the 4, that's 16, right? And that would be 4 squared. So this should be 4 squared in order for this to work out. But then z would be 2, but z and x are supposed to be distinct, so that doesn't work out either. So then we just go to the next one. So we have 2 to the y, let's see, 2 to the 3rd would be the next one, so that'd be 2 to the 8th. That equals 8 to the z. And, well, 2 to the 8th, that's 8 squared, right? Because 8 is 3 powers of 2 to the 3rd, right? So 2 to the 8th, that's 8 is 3 plus 3 plus 2. So we'd have 2 to the 3rd times 2 to the 3rd times 2 squared. So that's 8 squared times 4. And that's not a power of 8. Right, so we have 8 squared times 4 is equal to this 8 to the z, that power of 8. That's not going to work. Right, so this didn't work, this didn't work. And then we try one more before we get too frustrated. 2 to the 16 equals 16 to the z. And this is going to work because 16 is 2 to the 4th, right? So I can take this 2 to the 16 and write that as my 16 is 4 plus 4 plus 4 plus 4. And that's going to be 16 times 16 times 16 times 16. That's 16 to the 4th. And so we see that does work. So our x is 2, our y is 16, and our z is 4. So we have these three distinct integers greater than 1, and x to the y is equal to y to the z. So the proof of our conjecture, I guess we can elevate this to a proposition. So the proof that the conjecture is true is to consider x equals 2, y equals 16, and z equals 4. And then, well, we can't just say that. We have to show that it actually satisfies the property that we're claiming. And so we just check that, let's say, just be clear about this, the x to the y, then that's 2 to the 16. And that, I'm just recapitulating the argument down there. So that's 2 to the 4 times 4, which is 2 to the 4 to the 4, which is 16 to the 4. And 16, remember, that's our y to the 4. Well, yeah, so that's our 16 to the 4 is y to the z. So we find that x to the y is equal y to the z as claimed. Okay. Okay, as a last example, we'll consider the following conjecture. The conjecture is that there's a real number x such that x to the 4th is less than x, which is also less than x squared. Okay, so it's going to turn out that this is false. So we'll have to prove. Okay, so this is false. So we'll have to prove the negation. Okay, so I guess to give yourself some idea that this should be false, you can think about a couple cases just to sort of shore up your intuition here. So for example, if x is bigger than 1, then x squared is bigger than x. But then x squared, which is x to the 4th, is going to be even bigger than that, right? So there's no way that's going to be less than x. So if x is bigger than 1, that doesn't work. And if x is less than 1, when x is less than 1, x squared is even less than x, right? And then x squared, which is x to the 4th, is even less than that. So in that case, you wouldn't have x squared being bigger than x. So you'd have it being smaller than x. And so you could, I suppose, do show that this is, you could do some kind of case-by-case examination like that to prove this. That's not exactly the way we'll go about it. So let's look at the negation of this statement. We'll prove the negation. So the negation. Okay, so this is an existential statement. So the negation would say that for all real numbers, it is not the case that x to the fourth is less than x squared. And so another way we can say this, so not the case that x to the fourth less than x squared. Let's unpack that a little bit. So these two inequalities strung together, this is just saying that x to the fourth is less than x and x is less than x squared. And so this negation is going to be an or statement. So we're going to have the negation of the first one or the negation of the second one. Okay, so the negation, so we'll rephrase the negation. For all real numbers it is true that x to the fourth is greater than or equal to x, or x is greater than or equal to x squared. Okay, so to disprove this conjecture, we'll prove the negation. Okay, so proof of the negation. Okay, so let x be a real number. Okay, so we have to prove one or the other of these things. So here's a nice trick for when you're proving an or statement. You can basically assume that one of the things is not true and proceed from there. So let me make that clear how we can do that. So for x being a real number, so let's focus on the x greater than or equal to x squared there. Right, so for any real number, I mean, it's either the case that x is greater than or equal to x squared, or it's not, right? So it is either the case that x is bigger than or equal to x squared, or x is less than x squared, right? One or the other of those are, those are, each of those statements is the negation of the other. One or the other of them must hold. Right, so in the former case, we're done, right? Because we're supposed to be showing this or statement. So all we need is one or the other of them to be true. So in the former case, we're done. Right, that proves what we were trying to show. So basically, we can just assume that that's not the case. So when you need to prove an or statement, you can basically just proceed directly to assuming that one of the conditions does not hold, and then prove the other one, right? Because that's essentially what we came down to here. We're allowed to assume here now that x is less than x squared, and then we just have to show that x to the fourth is greater than or equal to x is the case. Okay, so assume the latter. I.e. that x is less than x squared. Now what we want to do is get x to the fourth involved here. So the natural thing to do would be to square both sides of this inequality. But we have to be just a little bit careful there, because we can only do that if we know that our x is non-negative, right? So So we're going to have sort of two cases from here now. One is going to be the case where x is negative, and the other one is going to be where x is greater than or equal to 0. So if x is greater than or equal to 0, then we can square, sorry, that's an A and that's an R, square both sides of this inequality and find that x squared is less than x to the fourth. Okay, and now all we have to do is combine, so now you just sort of concatenate the two inequalities, x less than x squared less than x to the fourth, that says x is less than x to the fourth. So combining this with x less than x squared yields x is less than x squared is less than x to the fourth. So x is less than x to the fourth, and in particular, so we see that x is strictly less than x to the fourth, but in particular that says that x is less than or equal to x to the fourth. X is less than or equal to x to the fourth. Okay. So that was in the case where x is greater than or equal to 0. So if, on the other hand, x is less than 0, so if x is less than 0, well, then just use that x to the fourth, that's x squared squared, and squares are always greater than or equal to 0. Right, so x to the fourth has to be greater than or equal to 0, and combine these two inequalities. So x is less than 0, but 0 is less than or equal to x to the fourth. Right, so again, we find that x is less than or equal to x to the fourth, as claimed. Which completes the proof. Okay, so that's a proof of the negation of the statement in the conjecture. So that's a disproof of the conjecture. Yep. Okay, so there's an so this proof I just gave here is not in the book. The book, I think, has some kind of misprint in it, because the book gives one proof of this, one disproof of this conjecture, and then later says that it's giving a disproof of the conjecture in a different way, but it's really look at it, it's exactly the same proof that he already gave. So I think he meant to put in a different proof there, but somehow got confused. So the same proof of this is in the book twice. So I came up with this alternate proof, which I think is probably more what the book had in mind as the initial proof, and then this next proof I'll give is the one which is duplicated in the book. So here's another proof, another disproof of the conjecture. So a disproof of this conjecture, so this statement P. So a disproof of it is a proof of not P, right? But one method of proof that we learned is proof by contradiction, right? So if you're trying to prove something, you assume the negation of it, and see that that entails a contradiction. Right, so in this case, to disprove our conjecture, right, so maybe I should write this down. So to disprove the conjecture, we want to prove not P. Right, so maybe I should be clear about this. To disprove the conjecture statement P, we want to prove not P, right? Which we can do by contradiction, i.e., by assuming not P, right, and deriving a contradiction. But not P is just the same thing as P. Right, so to disprove a conjecture, so this is summing up. So to disprove a conjecture, oh, I don't know what's happening to my penmanship. It's really gone out the window here. To disprove a conjecture P, it suffices to assume P and find a contradiction. Okay, so if you have some conjecture, it's often, it can be helpful to just assume your conjecture is true and see if that leads to nonsensical conclusions. Okay, so that's a technique for disproving a conjecture. Okay, and it's often sort of useful psychologically if you have some conjecture and you believe it's true, right? If it feels sort of comfortable that it's true, then it might be sort of easier psychologically to navigate the hypothetical world in which that P is true. And so if you can navigate around in that hypothetical world until you derive some contradiction, then that yields a proof that the conjecture is not true. All right, so we'll give another disproof of the conjecture. So here's the disproof of the conjecture. Assume there does exist a real number x such that x to the fourth is less than x is less than x squared. Okay, so the first step of our proof here is rather sensibly we're going to divide by x, and we just need to know that x is bigger than 0 for that, and that's easy because x is bigger than x to the fourth, and x to the fourth is bigger than or equal to 0 since it's a square. So since 0 is less than or equal to x to the fourth, we see that 0 is less than x. So we can divide by x and obtain x cubed less than 1 is less than x. Okay, so that's the first step. And then the next step is we're going to subtract 1 from everything. So subtracting 1 from everything yields x to the third minus 1 is less than 0 is less than x minus 1. Okay, and then the basically the last step, so our x to the minus 1, well, sort of close to our last step, the x to the minus 1 is bigger than 0, so I can divide by that as well. So now dividing by x minus 1, which is legitimate because that's greater than 0, as that one inequality there says, gives x cubed minus 1 over x minus 1 is less than 0 is less than 1. Okay, so now we so what this did basically, to give you an idea of like why kind of we did this, is that this sort of gets all of the x's in one of the 3 slots there, so that it puts all of the x's together in just one of the slots of the inequality. So we have 3 positions in this inequality, but all the x's are in just one of them now. Okay, and the cool thing about this quotient here is that actually we can rewrite this as a much simpler expression. Okay, so I guess I can just write it down, but it's easy to see. It is easy to see that x cubed minus 1 over x minus 1, that's equal to x squared plus x plus 1, which you can do by polynomial long division. You may have learned that in high school. And if you've never done polynomial long division before, you can see that this is true just by, so let me see. So it is easy to see that we have this identity by just verifying, by multiplying out x minus 1 times x squared plus x plus 1. And seeing that 1 obtains x cubed minus 1. In fact, we've met this identity before in workshop. You might want to go back to one of your workshops. It was the first problem on a workshop where we showed that x to the n minus 1 is equal to x minus 1 times x to the n minus 1 plus x to the n minus 2 plus ... plus x plus 1. So that's something you've actually proved that before. All right. I outlined the proof with some hints, and you completed the proof in workshop. So this isn't entirely unfamiliar to you. Okay, so nice little application of that. Right, so where were we? Oh, yes. And now that we have that, so thus we have x squared plus x plus 1 is less than 0, but this makes no sense because x is greater than 0, right? We have x is greater than 0 up here. But x is greater than 0, so clearly x squared plus x plus 1 is greater than 0. Right, in fact, it's even greater than 1. Must be greater than 1. It's greater than 1, which is greater than 0. right? So these two things can't hold at the same time. So this is a contradiction. Okay. All right, so believe it or not, that is essentially the entire contents of chapter 9. So we are going to stop there.